I don't need to stop recording. Thank you. So we're going to look at eccentric symmetrical loading first. Okay, so I'm going to look at this diagram. So now, can anyone tell me at which point will our structure fail? Is our structure going to fail at point A, point B, point C, point D, or point E? Anyone, please? No takers at all? Yep.
I'd say D and E.
So you're guessing between point D and point E, right? Yeah, you're not wrong. Yeah. So where it will likely, if the material is homogeneous, it will fracture here. That's where it's going to fracture. Okay, that's where it's going to fracture. So a very important thing to take note is how we translate a structure at figure A, and we divide them up into two. So now at figure B, where I'm highlighting now, when we divide the two, we only see point A, point D, and point C. Okay, so where a lot of us make a mistake is this. Okay, so when we take point C, so point C is our point of interest, right? Point of concern. So we have to figure out the direction of the forces and the moment that's acting at point C. Okay, so what do I mean by that? If you have a load P over here, okay, at point C, you also have a load F acting on the opposite direction based on Newton's third law. Okay, so Newton's third law, action equal reaction, same in magnitude but different in direction. So the point of concern at point C is where we're going to analyze our structure. And given P prime, like what you see over here, what we realize that over here we have a perpendicular distance. Okay, so this perpendicular distance is known as D. Okay, so what will happen whenever we have a perpendicular distance, we have an acting moment. So this is our moment, right? So again, action equal to reaction, same in magnitude, different in what? Different in direction, yes or no? So when that's the case, this is how your counter moment will act. Okay, so we know from here, if we were to sketch our deformation pattern, okay, if we were to sketch our deformation pattern will look like this. Okay, so I'm sketching in green. This is how the structure will deform. Okay, this is how the structure will deform based on the P prime multiplied by D. So when that's the case, what we have over here now, right? What we have over here, the top, where I'm highlighting in blue, this is, I call this is my point alpha, and the bottom part, this is my point beta. And we know, okay, we can identify at the top, right? This is the center of curvature. We are made aware that at the top, right, is going to be in compression, or for alpha is going to be in compression, and for beta is going to be in what? In tensile mode. Okay. Now, when we have eccentric bending or eccentric bending now, our formula slightly changed. So if we were to draw a transformation, so I'm going to sketch out our transformation over here. So this is our x, y, and then this direction, anti-clockwise right-hand rule. This is our rotation about z, right? So when that's the case, our formula, so we are looking at stresses in the x direction, now becomes px over a, right? And then if I were to follow the formula in the textbook, they will highlight that it's going to be minus mz, moment about z-axis, divided by second moment of area on the z-axis, multiplied by the y distance from the neutral axis or from the centroid. So this formula over here, that you see is for eccentric, symmetrical bending. Now, the first load over here that you see over here, the px over here, this is the same formula that you use for axial loading. Why that's the case? Because if you look at P over here, if you look at P with relative to point C, is in fact acting on the what? On the axial, on the axis. Okay, that's why we call it axial loading. And over here, this is due to bending moment. Okay, any questions so far?
Eugene, I have a question.
Yes.
Okay, so the center of curvature is below the beam, right? How
No,
come
so
the
sorry, the center of curvature I draw from to here is based on figure B.
Oh, okay.
Okay, my apologies. Okay.
Thanks.
Okay, my apologies. So we are, yeah, I should not make it so messy. Okay, so it's at this point. Okay, it's good that you clear. So it's real. So I'm going to box this up. Then I'm going to box this up. Okay, so there's the center of curvature. Any other questions? No, if anything that's not clear, just stop me. Okay, so what we see now, okay, like what I mentioned before, do not worry about the sign down here. Okay, do not worry. If in the formula or doing your exam you forget, or later on when you work in as an engineer you forget, don't worry about it. What do I mean by don't worry? Because we still follow the same. The top of the arrow will still be under what? Compression. The tail end of the arrow will still be what? So will still be in tensile. So if we were to look at stress X at point alpha, right? So alpha is at the top. So what we have is Px over A. So the F over here is also equal to our what? To our Px, right? So we know that from point C, Px is pulling the structure away, so it's in tensile. Okay, so plus by Px over A, and then alpha, which is at the top and is at the head of the moment arrow, so it's minus by mz over izz multiplied by y. Okay. Likewise, if we look at stress x direction at point beta, so this is also equal to positive mx over a, and because it's in tension or in tensile, it becomes what? Plus by mz over izz multiplied by y. Okay, so I don't want you to apply the formulas blindly. I want you to be able to what? Visualize. Now, the thing difference with eccentric loading is this. So if we were to have our if we were to draw a cross-sectional area. So now I'm drawing the cross-sectional area now. Okay, so this is my transformation now. So this is my y, this is my z, and this is my rotation in the x direction. Okay, so I'm just, for simplicity, our cross-sectional is a rectangular now. Okay, so we know, or what we usually do is we are aware that at this position over here, right, over here at this position over here, this is our position of our centroid, right? So this again is our y, and this is our z. So our centroid will have a certain distance. Okay, so our centroid will have a distance from here to here. So this is one of our distance of our centroid location. So from here to here. Oops, sorry. So this is our z prime. And over here, this is our centroid from here. And this is our y prime. Right. Okay. Before I go on, what I'm trying to deliver to you is this. It's not necessary your centroid is equal to your neutral axis. Okay, I repeat again, it is not necessary. Okay, I'm trying to drive this point that it's not necessary that the centroid is equal to the neutral axis. Okay, I want you all to meditate on this term. Okay, it's not necessary. So far, if you have learned the 2P04, it is always. Okay, so far. But for this case, it's not necessarily true. Okay, I want you all to follow. So why is that? So if we were to sketch, okay, so now we are going to sketch the stress profile. Okay, we're going to sketch the stress profile. Okay, we're going to sketch the stress profile now. So our x-axis is our normal stress. So this is our stress x, and our y-axis is basically y. Okay. So the first formula or the first term that we see under axial load, what we have is stress x is equal to px over a. So we're going to assume it to be in tensile. I'm going to draw this longer a bit. Okay, so that is our stress x. So what we have over here now is we have a load in tension now. Okay, so we will have a load in tension. So this is our load in tension. So this is where this is our stress x is equal to px over a. Okay, so this is our tensile load. Now, I position this is equal to 0 because of, okay, I draw over here, this is my 0 point because this is relative to the centroid. Okay, this is relative to the centroid. And to acquire the centroid, right? Remember I taught you on Tuesday how to acquire the centroid. So we were to review, if I were to quickly go over, right? Remember this was Tuesday's lecture. So this is how we locate. Oh yeah, it's a terrible mess now. This formula, right, over here is how we locate the position of the centroid by sectioning the cross section, by looking at the width and depth, finding the individual centroid, and then multiply all of them together, sum them, and then divide. Okay, so watch the video on this if you have forgotten. So coming back to over here, the centroid is acquired geometrically. Okay, the centroid, I will write down here, the centroid is determined geometrically. Now, this is just one of our stress profile. Then we have another profile coming in, and the next profile will be our bending moment. Okay, so again, this is my stress x, and then this is our y distance.